by David Glenar. Upper limits for a lunar dust exosphere from measurements by LRO LAMP. So David, whenever you're ready.
Okay. All right, let me. All right, it looks like we're waiting for the first slide here.
We see you and your slide, so you should be good to go.
Okay, yeah, I'm still waiting for that. Okay, here we go. Yeah, as everybody knows, and inside of a couple months, the LADEE mission is going to launch, and one of the goals of that mission is to do a very deep search for a lunar exosphere, actually a high-altitude lunar exosphere. But what I wanted to talk about is the fact that during the last couple of years, LRO LAMP has been carrying out an exosphere search as sort of a precursor to LADEE, and with really two purposes. One is to do an actual detection of a high-altitude exosphere. That's been a controversial subject in recent years. And the second is to do a definitive detection prior to LADEE, so that LADEE has some, you might call that a reference detection for the LADEE mission, because right at the present time, there's really nothing to go by except the old, very optimistic Apollo era estimates. Oh, I should also mention, yeah, this started out as a collaboration between LAMP team, and it's then a collaboration between the LAMP team members and a couple of us on Bill Farrell's DREAM NLSI node. Adobe quit. Okay, I guess I'm still on there. All right, here's a sort of a quick overview of the LAMP search program with the motivations behind it. The instrument, as everybody knows, LAMP, it's a far UV, very sensitive far UV slit spectrograph. And at the present time, LRO is now in its extended science missions. So you put those ingredients together, the instrument itself is a very good choice for trying to measure dust scattering from a very tenuous exosphere via forward scattering sunlight. And this has been the approach that we've taken. If you look at that diagram, that gives you sort of in a nutshell the observing approach that LAMP takes to detect a dust exosphere. About 4 times a year, of course, LRO is in a polar orbit, so about 4 times a year, LAMP is in a position where it's in shadow, but it can look toward the limb at very small solar elongation angles. So in other words, it can look through a long dust scattering path for maximum detection sensitivity. And that also helps because it lowers the shadow height. At the bottom of this slide, I also included, just in retrospect, our initial expectations for this effort were that we would see, even if LAMP were to observe a small fraction of the putative Apollo era dust exosphere, it would be a very strong signal, a very detectable signal. And Greg Delore sort of mentioned the bottom line here is that we made a handful of searches, and we're not talking in terms of definite detections, we're talking in terms of upper limits, okay? Because we're seeing what appears to be excess brightness. That excess brightness could be uncanceled stray light, and it's not at all clear that there's a well-defined dust signal there. This is a quick table which shows the searches to date. For these, the ones marked in red are the ones that are more favorable. The more favorable searches are, of course, the ones with a longer on-source integration time. That's the last column, and those with small solar elongation angle. That means that you look within a few degrees of the sun, you minimize the shadow height and maximize the forward scattering of dust grains. So that's sort of the search criteria. And these 4 observations marked in red are the ones that we've been analyzing. I won't spend much time on this, but real quickly, this is a sample at the right, it shows you, or at the left, it shows you a sample spectral frame from LAMP. This is the long wavelength portion of it that we're looking at. Left to right is wavelength. It extends to, coverage extends to about 195 nanometers or so. You see the other axis is the slit axis. You can see the very strong Lyman alpha line. So I've shown in this little example, I've shown the limb. A lot of that light that appears in that frame is grating scattered light. So the first step, if you want to look for dust, you look just above the limb and you look at long wavelengths where the solar spectrum is getting brighter. The dust signal is just, you expect to see a very weak remnant of the solar irradiance itself. So that's the search criteria. To subtract the background, I've pulled out one row there. You have to do a sky subtraction, and then you look for what's left. And you hope to see in that residual some weak remnant of the solar spectrum. Okay, this is, let me back up one. This is one piece of the data acquisition. You're not really interested, you're interested in the dust spatial signal. You're not interested in the dust spectrum because it's a color. So you co-add in wavelength and to build up signal to noise, and you add the many seconds of the integration time together to maximize the detectability. And here's the result. This shows those 4 observations that were marked in red. The vertical axis is excess brightness, and the horizontal axis is sort of like tangent height, the distance above the terminator. And 3 out of 4 of these observations, you see an excess light signal. And so now the question is, you've got this excess light. The uncertainties from topography and from pointing and from the spread and intensities are quite large. These are sigma 1, sigma 2 types of measurements. That could be partly dust. It could be all dust and stray light, or it could be all scattered light. It's very hard to say. It's useful for an upper limit. So the next question is, how do you assign an upper limit to this? Well, you need a simulation code. And if I go to the next slide, well, I'll just describe the approach quickly. Our approach is to take clusters of points that look like they're coherent and together, and use a simulation code and put that model to the code, and then see how much dust that corresponds to. This is a quick overview of how the simulations work. We have the complete detector pointing file matrices on the one side as a function of detector position and time. If you then assume a trial dust model, you put those together and it gives you the line of sight path integrations. On the other side, we need the per grain scattering. You see that on the other side, that's taken from the solar spectrum, source solstice, et cetera, et cetera. And you put those together and you come up with a trial simulation. You do the wavelength summation followed by the time averaging, compare it with the excess light measurements. And basically, it's a 2-parameter, N0, H, and H are almost independent. So it's very easy to walk in the surface dust concentration and some estimate for the scale height that matches your data, and that's what we've done. Here's the 3 observations that had non-zero signal, and what we've done is just place these models over those data clusters to get some idea of the dust upper limits. That turnover is shadowing that you see close to the surface. Again, this is the same axis of brightness and distance above the surface. The grain shadowing depends on the specific geometry. But what you see is we hit kind of a characteristic upper limit, something like extremely small surface dust concentration, something like 10 to the -5 per cubic centimeter. Possible scale heights of 5 to 10 kilometers. That part, this assumes 0.1 micron dust grains. So a very small upper limit, which is another way of saying that LAMP is a very sensitive a very sensitive probe for a dust exosphere. The next question is then, let's take these and ask, what's the implications of this very low concentration for the LADI UVIS dust search? I mean, how good can UVIS do? What we're looking at here, the black traces are these upper limit models. It's the same model, it's just 10 to the minus 5 and 10 kilometers at a few different, very close to the limit, a few different solar depression angles. So generically, it's what UVIS would look like just after the sun goes below the horizon. And down below that are the UVIS sensitivity limits that were measured using the engineering test unit. Those numbers have actually improved a little bit. Tony Copri mentions with the flight unit. We haven't put those improved sensitivity estimates in there. Bottom line is there's still a margin between the between the LAMP upper limit dust detection and the detection capability of UVIS, and that margin gets even larger as you co-add in wavelength, because for this kind of measurement you don't need spectral resolution. There's one sleeper here in this whole problem that's getting recognized, and that is the intensity of coronal zodiacal light. At that close to the sun, you see the relative intensity, well, you see the absolute intensities. It's 1 to 2 orders of magnitude brighter than these, or at least 2 orders of magnitude brighter than these upper limit models. So if you try to dig really deep, if you integrate co-add and wavelength, at some point with any detection, you're going to be limited by small fluctuations in the CZL, or it's more complicated than that. There's the F corona, there's the K corona. They have different spectral character. So there are going to be these second order complications that may ultimately limit the dust sensitivity of UVIS. That remains to be seen, and these are all open questions. And these are things that we're going to be exploring, and especially the CZL. We're looking quite hard at that to try to improve the CZL models and subtract them from UVIS data when it does appear. Let me just go to my conclusions. All right, so just what I've always mentioned, one takeaway from this is that upper limits seem to be like a surface density 10 to the minus 5 per cubic centimeter. That's in terms of line of sight abundance, that's about 100 grains per centimeter squared. That's an extremely small cross section when you think about passing through a long line of sight. What is the source? What is the reason for the discrepancy between this and the Apollo era? One possible explanation is meteoroid streams. They're sporadic, and there's a very large dynamic range in the meteoritic flux from one time to another. LAMP has not. Tim has looked at the LAMP search dates. They have not coincided with any streams of any significance. Bottom line, LAMP would. LADI UVS still has detection capability, but CZL is going to complicate that dust search almost certainly. Well, okay, thank you.
To remind folks that are listening, if you have any questions or comments for the speakers, please enter those into the chat window, and then we'll address as many of those as we can after each talk. David, I had a quick question for you. Through coordination with LADI, is there any possibility of synchronous observations between LAMP and UVS?
Absolutely. There was a joint meeting about a month ago between the LAMP team, and Tony and Greg were there, and that was the first probably of several planning meetings for exactly that. So the answer is yes. There's going to be an intense coordination during the overlap of those two missions.
Great. Thank you very much. We have one question from online. What shape do you assume in the grain scattering model?
Yeah, that's a good question. What you might have noticed, right now we're using Mie scattering, but we've also, several years ago, there was a paper by Dennis Richard. We compared Mie scattering for lunar lunar exosphere applications with discrete dipole. And we've created a bunch of shape models and done the scattering comparison with them, compared that with me. And that's in a 2011 Planetary Science issue.
Great. Thank you very much. If there are any additional questions,